Okay, so make it something like this. And let's put an epsilon. Yeah, 0.25 meters. So it's it's kind of similar to what we did in our second lab or third lab, but slightly different dimensions. Try to get a slightly higher capacitance. And let's make epsilon . Oh, how about 2.6 times 10 to the negative 11 squared. So, first of all, just as might as well just figure out what the dielectric constant is, and ultimately, either way, you want to approach it. What is C? This guy. I'm going to call it C1 because we're going to ultimately I want to do some stuff with this, and I figured the best way to do it is just heuristically sort of piece through it. Okay, so give me some kind of number for this thing. I'm all charged up today. Only my brain felt like my pen's on. Okay, so if I want to figure out my dielectric constant, I take my effective permittivity constant and divide it by epsilon naught. So, try to make the numbers look something like 3. 2. What?
94.
Okay, so 2.94, and capacitance says for this case, we take the effective epsilon, we multiply it by the surface area and divide it by the width between the plates. I'm just going to call it D1 for now. Just so we get a capacitance of some. Pardon me? A little better than what we had before. So about 36 nanofarads. So let's just keep asking some questions. What Q would be charged on this capacitor? So let's just say a potential difference of 25 volts. Basic question.
Yeah.
So Q1 would be C1V1, or this crazy number times 25. So somewhere, give or take, around 0.9 or so times 10 to the negative 7.
9.0.
Okay, so I got a lot of things I want to do with this, but just keep asking some basic questions here, because there's a lot of little subtle things that relate to this. This is the easy part, right?
So, how much energy is stored? Probably knew that question was coming, maybe. So the energy in this capacitor would be 1/2 C1 V1 squared. So 25 squared. Divided by 2. By the way, we made this point out. These are kind of review questions. This is not where I want to ultimately going with this. I got kind of some ideas in there, which is always a screw. That thing. Yes, so what is it?
Nothing.
Oh, you're just saying, yeah, it's a bad thing.
I'm just paying attention and,
Oh.
you know.
Lock in, man.
That's right.
1 times 10 to the 5.
Comes into the fifth, negative fifth.
It's 4.5 times 10 to the negative 7 times 25. So whatever that is.
So 101.2 times 10 to the negative fifth.
Oh, 4 point. Sorry, what?
What's it come out to then?
Uh,
Okay, 1.12. I was thinking 1.2, but good enough. Okay, so those are
Is that what you got?
basic questions.
I got a grade for it.
Now, let's kind of extend it conceptually and quantitatively as well. This not?
Let's not.
No, I think this is a good thing. We're gonna get to solid state at some point, so you'll need to think about this. How, brown cow, sorry, I guess I forgot the noun, didn't I? How does this Q1 compare to a same delta V charged capacitor air-filled of the same dimensions? How would they compare?
Well,
Q should be higher.
it's not one.
Oh, yeah. Q's lower.
How would we set it up?
Well, first one, you gotta figure out the capacitance.
Yep. So now we've got an epsilon naught A over D. Get our new capacitance.
Are you really gonna calculate that?
You don't really need to do a lot.
Could we say that all of the things being equal, these are the things I just want to kind of relationally think about. If the ratio of C1 to C air, smell that fresh sea air, should be related for the same V, Q1 to Q in the air-filled capacitor. Is that reasonable?
Yeah.
Moving to
Huge.
Yeah, it works, right? Which would be epsilon A over D
I guess I would have just done.
divided by epsilon naught A over D. So I just call it this. which would correspond to the dielectric constant. So, feel free to do the calculation, but don't need to.
Well, you know, I would have done the calculation, saw it was the same number, and then came to this realization.
Absolutely, that's okay too.
That's why we're here.
Just took a longer ride. I'm not that quick on the draw, guys, okay?
So, most of the time, just going all the way back to the game here, most of the time when you compare quantities, you typically do them as ratios.
Okay.
Never do differences, usually compare as ratios, because differences don't mean anything until you have a sense of how the magnitude, how that difference is relative to the magnitude of the quantities in question.
Okay, just want to double check that's epsilon effective, right?
Yes,
Okay.
divided by epsilon naught.
Okay,
And
cool.
epsilon effective is K kappa
Gotcha.
times epsilon naught.
Okay, just making sure.
So it just sort of falls out.
Okay.
Now, here's where it kind of gets a little bit interesting maybe. What is the ratio of the electric field of the charge in the charged capacitor to what it would be if it were an air-filled capacitor?
Well, for particle plate capacitors, electric field is just sigma over epsilon. So compare that to sigma over epsilon naught.
Right here, what is it? What's E1 mean?
Absolutely, very valid way to do
Is
it.
that electric field?
Multiple
Oh,
ways to
okay.
do it.
Alright, alright.
I might have just said it, just to remind myself how voltage is related to field and capacitance. I might just have easily said, well, E1 should be related to V1 divided by D in magnitude. I'm going to call it delta because it's the difference between the voltage on either plate divided by the separation distance. That's what the electric field is going to be.
Call it EK.
And E air is equal to, oh, look at that, it's similarly charged voltage. And it's the same separation distance. So, when you have a dielectric, the charged Q is greater than what it would be if it were hollow or filled with air. But the magnitude of the electric field between the plates is the same. Why? How can this be justified? How might we even argue that it might be required?
Because the charge can build up more?
Hmm?
Because the charge can build up more?
Why? Same electric field,
Slow down the...
same electric field, same voltage. Obviously, the charge will build up more. We've already said that, it is. But can we explain physically how that can happen?
The change in the charge is compensated by the change in the dielectric constant.
That's a beautiful way of talking around the issue.
Is there a, do the charges get induced in the dielectric? And that creates a electric field that counteracts the greater electric field that would be there if the charges were.
Yes and no. No charge builds up inside the dielectric. It's an insulator, but it does
The pole.
separate, it polarizes.
Right, separate, right.
Yeah, it doesn't actually get induced,
Right.
but you have an induced polarization. So, let's come back over here and look at this. This is just kind of an interesting little features. I'm only gonna draw one in here, because I don't care about all the rest of them. If this is the positive end, and this is the negative end of this charged capacitor. When it's air, it's this. When it's filled with something else, now you've got little atoms in here. How does that separation of charge, how is it directed? What direction does it point? What's the direction of the electric field? Maybe just start here. What's the direction of the field between these plates?
Positive to negative.
What's the electric field in here? So, what's the direction of the charge separation inside those little molecules?
Hmm,
Positive would be down and the negative would be up.
right.
That whole moving sort of line.
Yeah, they all think of it as the dipoles aligning in the electric field, or think of the positives as being pushed in the direction of the electric field and the negatives being pushed in the opposite direction. So we're thinking about this, I'll just draw it as one big piece. It's kind of essentially like this. What does that say about the electric field associated with the separated charge?
In the opposite direction.
That's how it builds
This
up.
electric field is going to point this way. So I'm going to call it induced.
You have particles in the air too, so it's
There, first of all, the density is so low. You absolutely do. But the density of it is so low that for all practical purposes, it's negligible relative to a vacuum. It does exist if you go out to 4 decimal places. Just sort of reality check. In vacuum, epsilon naught, the true value, not epsilon naught, excuse me. In vacuum, kappa is 1. In air, kappa is about 1.00054, something like that. So you got to go out here, or round it up 1 point here, before you can even see it. It does matter. It absolutely matters, but it's not highly significant. So, what does this tell us? The electric field here just is. The electric field over here, you've got a situation, right?
It's greater, but the sum of the two is equal to the one on the right.
So if we thought about the electric field, it's the same on both sides, but it's going to have to be equal to whatever the electric field would be in a vacuum. When you subtract this induced electric field, you get the same total electric field. So really, if you think about it this way, it's the electric field across the capacitor, not including the dielectric. minus this induced electric field due to the dielectric. In other words, it has to compensate. It's the guy that has the monster truck. Because of the presence of this, you have to overshoot the electric field with charge, or you have to overcharge it in order to get the same electric field.
Wouldn't you add it then?
No. This number will be higher than this number.
Well,
In other words-
you could do a vector sum.
What's that?
You could do the vector sum. Then.
Well, it is a vector, so that's why I'm putting a minus sign in here. So, yeah, I'm sorry, yes, yes. So, I might have even changed to another color to sort of show us. So this is a weird sort of a compensation, because nature's fighting back, and so you have to overshoot, because the one thing that you can say with certainty, so in between here, it's almost like you've got an electric field due to the Q, as though there's no dielectric. It's physically larger because of the vector difference, or the vector sum, between the two parts. Now, that's kind of an odd little phenomenon. And I should have guessed it this way. So you have this, and you have this equals that, if you will. Draw the same color. Some reason, even though I know you can't probably write in the same color. Okay. Basically that. Vector sum. So in other words, you have to use more charge build up because of this little back separation, because of the separation charge. So that's kind of an interesting little phenomenon. And that affects a lot of things in a big picture, right? It's nice to just talk about charges being left alone, but the reality is you've always got this separation effect of charge whenever you put charges near other charges, even in neutral situations. And the question becomes, among other things, what is this dielectric constant? Because it affects how the charges separate, and ultimately the requirement of extra charge to achieve the same goal. So all things considered, two identical capacitors, one with air, one with something else. For the same amount of voltage, you will always have the same electric field between them. You just have more charge to produce it. So the sliding scale is how much charge you need to get the same effect, whether or not there's something in between. That's an interesting thing to sort of point out. Okay. Any questions on how that works out? That's I always found kind of a cool little phenomenon.
So say you had a capacitor just on a battery or whatever, and you put in a dielectric, it like pulled more charge out of the battery
You betcha.
to the capacitor? And then would you use that, like, you could then discharge more charge or something?
You betcha.
Like that?
The more charge you have on that capacitor, the more you can release when you remove the battery and discharge it. Here's another thing, just sort of hypothetical. They hold different amounts of energy. So, taking your point, if you had an air-filled capacitor, and you put a dielectric inside, it would fill up more charge as you're pushing it in. And more energy gets stored. You gotta do work to do that. It requires work to push that dielectric in there. Because as you're pushing it in there, it's pulling charge. You gotta transform that work that you produce into this field. So there's some interesting aspects of this. It would take work to take an empty charged capacitor with air and physically push a dielectric into it. Just want to push back. You have to push that energy in, if you will. There's a work aspect to it.
If you took the dielectric out after it charged up, would all that charge go back to how it is normal levels?
If you're keeping the voltage fixed.
Right. If you like
So
charged
you
it up.
have to keep
and
it
then-
attached to a battery. As
and
long
then-
as you kept it attached to a battery so that the charge has a place to go,
and then you were-
absolutely.
But
If
you, like,
not,
took
then it
off
would
the
just lower
battery-
the voltage. The voltage would drop across the capacitor, or rise when it rains. I'm gonna think about that now, C times V. You got more charge, your voltage would go up. Relative to an air capacity. But it would require work to pull it out.
So you said,
I think I've got that backwards. It would take effort to pull it out. Pushing it in would actually be self-inflicting, or
It would like suck it
it
in.
would suck it in, because of the direction of the charge separation. So I've drawn a picture, it's, you can see backwards.
so we've got this equation here for the energy stored on the capacitor, 1/2 the capacitance times the square of the voltage.
Mhm.
So work is required to push this dielectric in, but the capacitance and the voltage doesn't change.
When you take the dielectric and push it in. Oh, and capacitance does change.
Didn't we just work all of this through with the capacitance being constant?
Well, but that's not the case if you're physically pushing something into it.
Okay.
Now the rules change. Because now you've got a situation where you've got a region that's air-filled, and there's an electric field, and then a region that's dielectric filled. And that's gonna have a different.
Yeah, I was just trying to make sure that it wasn't contradictory.
No, it will not be constant, it won't be contradictory. Anything that's contradictory is my own poor usage of language.
I mean, if you're doing work, there has to be energy going somewhere.
Yes.
So,
Now, but let's think about this for a second. Let's just keep adding to this, because we're gonna get to where I wanna get to now. So, another extended idea, and I'm gonna write this down, but we're gonna use the same basic premise. We know something about what's going on here. Oh, what's the best way to do it? Do I want to split it in half? Yeah, let's just put it in. So let's take the capacitor. Same one, same plates, I should say, not same capacitor. Same dimensions. This time, I'm going to fill it halfway. With the dielectric, leave the other half in air. How much charge will this thing hold now? And to keep the charge, keep the 25 volts between them. So, let's ask some questions. What is E in the dielectric region and in the air region, respectively.
Yeah, that's the same.
They have to be the same.
Right.
Because if you've got a fixed voltage, you've got the same separation distance, V divided by D, your electric field. So the electric field is the same regardless of which side you are in. This being the case, then, this being the case now, how much total charge, or how much charge, I should say, has to be stored in this region in order to maintain the electric field here? And how much charge has to be stored over here in order to maintain the electric field on this side? So let's call this over here Q1, and over here it's Q2. This guy in here. On the one side, Q1 is going to be equal to the effective capacitance in that region times the voltage across that